So as promised, I wanted to give you some examples, some further examples from your textbook. So the first set of three is on page 99, numbers 11, 13, and 14. I'm going to go through these and give you a brief little drawing for each one, I suppose, as needed. You notice on these first ones, they actually show you the equations that they recommend you use. Very useful, I think. 11, calculate the increase in potential energy, and this is gravitational potential energy, as you'll see, when a 20-kilogram block of ice is lifted, so here's our ground level, lifted a vertical distance of 2 meters. So mass is 20 kilograms. It gets lifted to a height of 2 meters. Let's put 11 up there. Well, you have gravity, of course, 9.8, and I'll just put the units here. Don't ever let them confuse you. Meters per second squared. That's acceleration units. And you just carry out the calculation. GPE is mgh. That's 20. They're already in the correct units, so I don't have to worry about being very careful with those. Times 9.8 times 2. Looks like 40. It's going to be a little bit less than 400, probably 392. Let's see. 20 times 9.8 times 2, 392. I don't know where I was getting 492. Yeah, 392. And these are joules. The good thing is this is all recorded, so you can go back at any point and talk about them or think about them a little further. Calculate the kinetic energy of a 3-kilogram toy cart that moves at 4 meters per second. So here's the cart. Mass is 3 kilograms. And it is moving with a speed of 4 meters per second. The velocity, I was about to say, will be 4 meters per second to the right, because it has to have direction. Again, the equation, KE, 1/2 mv squared. I always put 0.5 as my 1/2. Mass is 3. Don't forget the squared. Right? So 0.5, 3, that becomes 16. It'll be 8 times 3, which is 24. 24 joules of kinetic energy. If at any time you guys catch mathematical errors on my part, you can let me know, but don't let it shatter your reality. It's pretty easy to trace. You just follow the work. Okay, so for 14, calculate the kinetic energy of the same cart moving at twice the speed. So again, you can go back through with 8 meters per second if you like, but since it's squared, if you double the speed, then you quadruple the energy. So 24 joules times 4, 96 joules. The beauty of this format is, as I said just a few moments ago, that you can really go back. I don't have to spend too much time on each one because everything's there in front of you. And then if you have a specific question, you say, Mr. LaFanzia, that number 44 on page 101, I didn't quite get that. I got lost here. And then it's very easy to go back and help you out. So on page 101, number 43, they start to get a little more complicated. You have a golf ball and a ping pong ball, and they're both moving with the same kinetic energy. Can you say which has the greater speed? And explain in terms of the definition of kinetic energy, and then there's another part to it. So ping pong ball, golf ball. I'm going to shade in the golf ball. They're basically the same size. The golf ball is not hollow, not made out of a thin plastic shell. And if they're moving at the same speed, remember kinetic energy is 1/2 mv squared. If they're moving at the same speed, then that means that we have to compare the masses to see if there's a difference. Well, the golf ball has a big mass, and the ping pong ball has a small mass. So the kinetic energy of the golf ball would be greater, all speeds being equal. Now, looking back, the question itself actually says that the kinetic energies are equal. So, I think what I'll actually do is, that was a nice little discussion. That was a good pre-question example. Okay? So just move this off to the side in your minds. Call that an aside. I didn't actually answer the question that the book was asking. I don't want to confuse you guys beyond that. So the ping pong ball and the golf ball moving now with the same kinetic energy. There we go. If the kinetic energy is the same, then since the mass contributes so much, the ping pong ball has to be moving at the greater speed in order to help counteract its low mass. So in this case, let me just scratch that out for you because we're on a different section, different discussion rather. The ping pong ball must have a greater speed. Again, because if it has such a low mass, if they're really going to have the same kinetic energy, it has to make up for it with a higher speed. Now the second part of that says, similarly in a gaseous mixture of massive molecules and light molecules with the same average kinetic energy, can you say which have the greater speed? Well, sure, if they have the same average kinetic energy, meaning the same temperature. If you have the lighter molecules in a gas, they must have a faster rate of motion, right? They must have a faster speed. Again, in order to make up for their lower mass. Assuming, again, they have that same average kinetic energy. So 44, this one is always a good discussion point. Does a car burn more gasoline when its lights are turned on? I like to ask that question now and then of groups of people. The idea is, yes. Okay, you are charging, well, here's a battery, and the battery gets charged. All right, there's a series of, well, it's an alternator basically, and a lot more goes into it than this. But your battery gets charged, and it runs the lights. And if whether the battery's on, whether the engine's on or not at the time, this battery needs to continually be charged. And so here is your engine. Okay, it's a Geo Metro with an inline 4. Anyway, you have gas usage. So energy is boring. If you're using energy here, then you have to make up for it somewhere else. All right, it has to have come from somewhere. You do not create energy out of nothing. So it says, does the overall consumption of gasoline depend on whether or not the engine is running while the lights are on? Besides any small technicalities, not really, because this battery is going to be low if it's off, and if it's on, then it's just going to continually be charged, basically trickle charged from the alternator system. And 50 on page 101. Can something have energy without having momentum? Well, yeah, sure. Right? Momentum means you have mass and you have a velocity or speed, if you will. And so you'd have a kinetic energy, but things can have energy without moving. All right, here's an example. Here's a rock. It's not moving, but it has gravitational potential energy, according to my frame of reference here. Not moving, right? 0 meter height. That's just one example of many. A polonium object, right? Plutonium, polonium, americanium, nuclear energy. Now, you might really want to look at this on the small scale, and you might confuse yourself. Yes, I know that everything has thermal energy, so it's kinetic energy on the small scale, which means the objects themselves that make it up have some momentum, but we're not talking about that. We're talking about a large-scale object. So then it says, can something have momentum without having energy? No, absolutely not. If you have momentum, that means you're in motion, and you must have kinetic energy. So you cannot have momentum without also having kinetic energy. So the last set of three, to help you out, is on page 103, numbers 11, 13, and 14. So belly flop Bernie dives from a tall flagpole. Here's the flagpole, here's the 0 meter mark. Let's assume that this is water. Let's say there's a little platform up there. Let's just imagine that one. And there's a GPE of 10,000 joules, or 10 kilojoules. Now at the bottom, the GPE is 0 joules. At the top, the kinetic energy is 0 joules. Right, just fell right off. And right at the bottom, the kinetic energy should also be 10,000 joules, right before they make that splash at their 0 meter mark. So show when the potential, his potential energy reduces to 1,000 joules, his kinetic energy is going to be 9,000 joules. Well, it's just conservation of energy, right? Let's pretend this is 9/10 of the way down. If GPE is 9,000 joules, then since total energy is boring, E total is 10,000 minus 9,000. We're left with a kinetic energy of 1,000 joules at that point. I'm sorry, gravitational potential energy. So this is the kinetic energy. Boy, that's frustrating. That was 1,000 joules of GPE. You poor guys. 1,000 joules of GPE. You're probably yelling at me. 1,000 GPE, and we're left with 9,000 KE. Now the fortunate thing is, not unlike college professors with whiteboards or with chalkboards, I can rewrite this. Okay. So again, 10,000 minus 1,000, 9,000 joules in terms of kinetic energy. And that only makes sense as you go down the spectrum. And then so it's compared with the height of the flagpole, how far above water level will Bernie be when his kinetic energy is 9,000 joules? Well, we've already determined that you're basically 1 meter up, or 1/10 of the way up. So if it were a 10-meter flagpole, it'd be 1 meter from the ground, but we're not told the height. All right, 13, home stretch. A lever is used to lift a heavy load. When a 50-Newton force pushes one end of the lever down 1.2 meters, the load rises by 0.2 meters. Let me draw this. Oh, that's horrible. There we go. That's a little bit better. Imagine a little seesaw. Okay. There's our fulcrum. There is a load here, a heavy load. I push down with some force, and we actually can divide this up into two sections. So here we go. Okay. We have the input section and we have the output section. Let me make this a little more sensible. There we go. Input section and output section. So we're going to go through 1.2 meters on the input section, and the force is 50 newtons. Now the output section, the force has to be 300 newtons, and the output is 0.2 meters. Now this is worded interestingly. You just have to show that the weight of the load is actually 300 newtons. So you have to prove this. Well, work in equals work out. Work is force times displacement, so the work in work in 50 times 1.2, and of course we all know what that is. Ta-da! See? As suspected. So 60 joules is the work in. We should, if this is an ideal situation, get 60 joules of work out. So go back to your little triangle for work. I told you could use this a bunch of times. And we're trying to find force. Force is work over displacement. 60 joules divided by 0.2 displacement this time. And that does in fact turn out to be 300 newtons. Again, remember, joule is a newton meter, so the newtons cancel out. And I'll just verify for you. See, 60 divided by 0.2, 300. Not a problem. So we've proven that. Oh, that was interesting. There we go. Proven. And the very last one, 14, it's the same idea. It shows that the force required to lift a piano is 500 newtons. There's a pulley system. Here is the piano. It's a baby grand. So the force in, again, here's our input side and our output side. The force in that we apply is the question mark. It's supposed to be 500 newtons, the book tells us. We have to prove it. And then we are pulling this through 2 meters, distance in. And then the force out, well, this is a, 5,000 Newton piano. That's the weight, and it's going to be lifted up 0.2 meters, 20 centimeters. It's not very impressive. So again, same idea, except now we have work out. And so the work out, 5,000 and 0.2, what was that? 1,200, let's see, 2 tenths, 1 tenth, 1,000. Yeah, 1,000, and I'll even verify it for you, just so you see it. I like to show things on the calculator just in case anybody wanted to see it. Go back and pause that frame if you want. Some people like it. Workout's 1,000 joules. So that means that the work in has to be 1,000 joules. So again, with our triangle, work, force, displacement. Trying to show that force is 500 newtons. Well, let's see, 1,000 joules divided by 2 meters. I really won't show that one at all. 500 newtons. Yes. Yes. Proven. And that's that.